Okay, so let's go on now and finish this proof. So I started proving this. So this is proof of general Poisson summation formula. So we can call it PSF as before. So the setting was like this. G was a locally compact abelian group. It's usually denoted by LCA capital, so I can just use locally compact abelian group. H is a closed subgroup. So we fix R measure on G, and we fix a R measure on H. So there's a little lemma that's kind of interesting. Okay, so I mean, before doing the lemma, notice you have an exact sequence like this. I can write additively 0, H, G, and G mod H, and 0. So this is an exact sequence in the category of locally compact abelian groups, an exact sequence. So the idea, as we discussed, idea of this general PSF is the following. Basically, you want to relate Fourier analysis on G to Fourier analysis on this two two parts, which is one is the quotient, one is the kernel, right? Relate Fourier analysis, as we discussed last time, on G to Fourier analysis on H and G mod H. I mean, a very simple, almost trivial example is the following. Of course, you can take G to be a direct product of two locally compact groups, right? For any H and K belonging to LCAs, you can take G to be H cross K, Cartesian product of the two. And then this sequence is a very well known, of course, is Cartesian product sequence, H cross K, and then K and Z. I mean, this is the simplest trivial case that there is no twist. This is like a vibration, right? So there is a twist here. This is like a base of the bundle, and fiber is H, total space is G. So this G is obtained by putting together copies of H according to the base, and there's twisting. So this is very complicated in general, but this is very simple. It's no twists here, Cartesian product. And for example, we know that the space of characters on this is Cartesian product of characters. So I mean, here things are very simple. I mean, essentially, characters is equal to, okay, so things like that. are true, but here things are more complicated and we want to understand the situation. Okay. So, but we have to start with choice of hard measures on G and H. Now, there is there's a unique, so there's this lemma now. There exists unique hard measure on G mod H, such that integration on G can be reduced to integration on these two copies, such that for any, say, F belonging to L1 of G, I believe L1 is enough, but if it's not, you're not happy with L1, you can take continuous functions with compact support. It still fixes the measure because that's dense and everything. For any F in L1 of G, you can write the following integral F of G dg. This dg is the hard measure that you started fixing there, right? Over G. We can write it. So now I have to, sorry, I have to get the thing, go to full screen. Okay, so maybe, okay, so such that this can be reduced as integration over, like it kind of twisted Fubini theorem, more or less. We can write this as product of two, double integral over this two things. So this is equal to, so I can write it as integral over G mod H over the base. And then there is integral over H, f of x H. Here is dH, and here is dx bar. So this dx bar is the hard measure that we are looking at on G over H. So this is the hard measure on G over H. So you have this function for any x, you find this element, you integrate against it, and this is well defined. Right hand side is well defined, and we can just. So this is a kind of Fubini theorem, kind of. Maybe there's one. I'm not sure. So okay, so this. But general properties of hard measure can be proved easily. That's not difficult. So that's question.
A question. So the choice of x within the coset doesn't matter.
It doesn't matter, right? Because we are here really choosing, or we are integrating at the end over G over H. So it doesn't matter. Yeah.
So is this like, well, the choice of x has to be continuous with respect to H, right?
No, because we are talking about measure theory, so continuity is not relevant. So this result basically says that as far as measure theory goes, I mean, these vibrations are like products. That's what it is. Let me draw a picture. Maybe you want to have this picture in mind. This is kind of picture that I use later on. So this is like maybe G, and there is this H here. There's this subgroup, and then we take its cosets. And so you project the whole thing. This is the projection pi over here is the space of cosets, which is G mod H. So basically, the integration over this can be carried by integrating over these pieces and then integrating over this. Yeah. So that's okay. So that's the way that I want to use the measure with this topic. Okay. Now another thing is that because we have Poisson theorem, so let me just write it next. Poisson theorem also fixes a measure, a hard measure on the dual group. That's what by Poisson theorem, which I did not prove, but I gave examples and things like that. So by Poisson theorem, this measure on there exists unique hard measure on G over H, but such that, of course, Poisson theorem holds. Okay, so the message is the following: that if you have hard measure on G and hard measure on H, then you get hard measure on G mod H, and also you get hard measure on G mod H dual. In a canonical way. I mean, there's no choices involved after fixing hard measure on G and on H. And okay, so yeah, that's what we need. I mean, in order to precisely formulate the theorem. But okay. So all right, now I can write the theorem again. So this is general PSF now. Given H subset of G as before, for any F in L1 of G, we have integral f of h dh, or h is equal to integral over, so I call it h star of hat of k. Maybe I write chi now, then d chi. Okay, so let me explain this H star, because we are not in like in the torus case, we are not in Rn, we are abstractly working. So what is H star? You see, the thing is, this H star is the set of all characters chi of G such that chi restricted to H is identically equal to 1, right? So these are, so all characters of G such that if you restrict to H, you get 1. And you can show that this is isomorphic to more or less, I think this is easy, that this is that one. So then when I write this d chi, I mean, this is the measure that, I mean, the isomorphism here is natural, right? You just send the character here to this quotient space. It descends to the quotient because it's on H equal to 1 and vice versa. So both sides are defined on this H star. Now you have to compare this with the duality that we have for lattices in Rn, where the dual lattice was defined as a sublattice, as a lattice in Rn again. But here the dual is not there. It's is really is in Gmod H dual, and all that. This is of necessity because we don't have. Okay, so that's the general statement. And so f hat, of course, is the Fourier transform of f as we define. Which of course was defined to be, so f hat is a function from the dual group g hat, I mean to C such that f hat of chi such that f hat I was equal to integral f of g of g bar dg over g. This is the Fourier transform of this element here. Okay, so both sides are defined now. So as I promised, let's just give you an idea of proof. The proof that there are two proofs for this, as I said before. One proof which is really what we need in order to go to the non-abelian case is the following. So just let me simplify things a bit. Just to simplify things, I'm going to assume that H is actually a discrete subgroup. Just it doesn't make any difference really, but it just helps with the notation to simplify notation really. Assume.
A question. Is the assumption here really that f is in L1? I mean,
Yes.
The possible counterexample that I have in mind is that say g is real numbers and h is integers, and then if I take a function from L1 of g, then it is basically undefined on integers. I cannot restrict because it's up to measure 0 sets. So
okay, yes. So you mean the left-hand side is not defined?
Well, yes. If I take an L1 function on real numbers, then the restriction to integers is basically arbitrary. And also, it doesn't have to grow, because if I have an L1 function on R, then it doesn't. It could be big even for large arguments, but on very narrow intervals. So it could be precisely on integers. So it could actually grow when restricted to integers.
I agree. Exactly. Yeah, there is, yeah, absolutely. I mean, if it is an integer in our case, so maybe I have to assume it's continuous. I mean, and with compact support or something like that. I mean, there should be some decay at infinity so that integrals are convergent. And so let me see if I have something here or not. Oh, yes. No. Okay, so do I have something? I don't have the exact conditions. Maybe we should just assume that it's continuous and then with some decay at infinity. So yeah, you're absolutely right, Ruba. I think let me just say just continuous plus so some decay, good decay. I mean, even the idea of decay is not very clear here because this is a general group. So what decay means? So you have to be, but there is an easy way to fix this. I'm pretty sure. Continuous plus good decay. So is that better?
Yes.
Yeah, but you have to you have to work this out a little bit. So there's some condition there. Right. No, thank you. That was a very good point. Yeah, excellent. The idea now, so now my simplifying assumption is assume H is discrete. Okay, so, oh, now, by the way, I was going to assume that G mod H is actually compact. So in this case, now the dual of the compact group is a discrete group. Since dual of a compact group is a discrete group. I mean, compact abelian group is a discrete group. So in this case, then basically what we have equality. Instead of integration, we have summations of both sides. So this becomes really like very similar to our original PSF. Then we get summation and we get summation. This helps a little bit. Really, it's not essential. This reduction is this assumption is not essential. I mean, but okay, just makes us understand the proof a bit better. Okay, now, as we did before, as in the case of, remember we had this proof of, I mean, some lattice inside Rn, right? So this was G, this was H, right? And G mod H, of course, is a torus. So for any, in general now, for any F suitable, so let us define an operator KF. Did I use KF or AF? What notation am I using here? So RF actually, yeah, that's a better notation, yeah. Let RF, we go from L2 of G mod H to L2 of G mod H. So this space has a Harnager now, you can take its L2. We define an operator from there to there by the following formula, Rf of phi on some class, some also is equal to integral over whole G f of y phi of x plus y dy. Okay, now all you have to do is to make sure that this is well defined in the sense that what we did here, you see under this map, so x bar is here, we just, you know, to find the values, we just, yeah, anyhow, so that's, this is well defined. So easy to check that it's well defined. Now we're going to show that this is actually an integral operator. It's an integral operator with a kernel that. So claim is that this is an integral operator. And to show that you really have to just write this integration, which is, by the way, is kind of convolution. you can write it as follows. So you can write it as f of y minus x phi of y dy.
So here f is a function on G or G mod H.
This f is a function on G. So f, a function on G. Remember, yeah, I mean, even in the statement, remember the statement was that for any function f on the big group, if you sum over this lattice is equal to another sum over its Fourier transform with respect to on G over the dual lattice, right? So it is that function that we want to prove the statement of Poisson summation formula for it, right? So the function is on G, yeah, f is on G. Take it continuous, e.g. f belonging to CCG. Yeah, just.
Maybe you can put a hat on x plus y if it is helpful.
Yeah?
Yeah.
Oh, yeah, okay, so we can put something. Yeah, okay, yeah, right. And this is also in the quotient, so. All right, so now this, if you write it like that, then this becomes, by our theorem that fixed the value of the R measure on the quotient, this is equal to integral over G mod H rather. I mean, sum f of y minus x plus h. I have to make sure that I'm not out of place. F of y minus x plus h, phi of y dy, h in h. So this integration is over G, but here we are, so what we are doing again, this is this big thing G, this is G mod H. We are integrating, I mean, we reduce, because I mean, here there's this discrete part, right? There are these discrete parts. We sum over them and then sum over. So this is like what we have in the case of gamma in Rn. That was similar. We found this kernel. So let us define k of. So we can just write then. We can write it as integral over G mod H. Kf x and y, phi of y dy. So this kf is this kernel. Okay, now this guy G over H is compact. And this kernel is continuous. I'm working with continuous f's. And f is, I mean, being a L2 is enough, actually, in general, for the statement I'm going to make. But here is actually continuous, and Kf is continuous on this compact space. This implies that Rf is actually indeed is a trace class operator actually. Liberation is not enough, sorry, is a trace class operator. So this is the operator whose trace we are going to compute in two ways. And the two sides of this equality gives you the two sides of the Poisson summation formula, right? So that's the idea. Okay, so Now, so next, compute a trace of RF in two ways. Via kernel F, and via its spectral decomposition. Via its spectral decomposition. Okay, so if you go by kernel, of course, trace of RF is equal to integral over G over H K, so KF XX or YY, I don't know, DX. So here, if you put Y equal to X, you're summing over this discrete set H. So this is equal to integral G over H, sum f of H, H belonging to H, and here is dy. But you see, this now is independent of Y. So you just pull it out, and this is compact, this Hahn measure is normalized. The theorem I said guarantees that this is normalized. So this is equal to, actually on the nose, is equal to sum f of H, H belonging to H. And this is exactly left-hand side Poisson summation form. Is the left-hand side of PSF. So for the other side, we just look at the situation as follows. So you have this L2 space, there's an orthonormal basis for this. Now, in the space, L2 H, there exists an orthonormal basis. So these are of distinct characters that belong to H star. Characters. So this is G mod H hat. So this is a easy case of Peter-Weil theorem. So this is Peter-Weil. I mean, the reason, so this is a group, this is the dual group, and we know that, I mean, characters form an orthonormal basis for a space of L2 functions on any compact group. And I'm assuming this is compact. And I have to assume this is compact also in the non-abelian case, which comes next, because in general, trace formula for the cases where the quotient is non-compact is much more subtle. I mean, you get continuous spectrum and all these things. So this is much more. So we are not going in that direction. We are just assuming. So this is the case. So then trace of this guy. So trace of RF is equal to sum this RF chi, where chi belongs to H star. mod H. So now the thing is, so this is sums of eigenvalues, basically. So these are eigenvalues. Now we claim that actually, so this is a claim now that a character is an eigenfunction for this convolution operator. And that's the last observation.
Sorry, shouldn't the summation be over the orthonormal basis, not the entire H star?
No. You see, H star is a discrete set because G mod H is H star. I'm saying is my notation for G over H hat. It's not. I'm not dealing with that. I'm not dealing with H hat.
Yes, but even if H star is discrete, like there will be many more characters in H star than the orthonormal basis, right?
No. The characters, I mean, I'm talking about characters that are killed by H. In other words, killed means the value is equal to 1.
Oh, it's not a vector space. Okay.
No. It's really like a discrete set.
Oh, so you're saying that H star really is an orthonormal basis itself. Okay.
Yes, exactly. The
Right.
summation is over H star. Exactly. Is that clear? Almost, yeah. Okay, so yeah, okay, so yeah. I mean, this is, but it's good idea to have that picture of lattice gamma inside Rn and the quotient and all. Yeah, there are some identifications that may, so this is the thing. So now the claim is that each character.
Are they actually orthonormal or up to some factor?
I think the choices that I have made, they are actually orthonormal. So they are not orthogonal. They are actually orthonormal. I believe so, but I'm not even. Yeah, I think I don't even need orthonormality. I just need the fact that these guys form a orthogonal basis, I believe. Yeah, it could be that they are not orthonormal, but they are certainly orthogonal. I mean, different characters, when you take the inner product, it gives you 0. They are orthogonal to each other, and they form a basis. They form a basis, yeah. They must be orthonormal. Yeah. Yeah. Right. Okay, so each character chi is an eigenfunction for Rf. So you see that it's not difficult now. So so let's compute. It's a very easy computation, except for one fact, which is kind of, so Rf of chi, it's computed on some x bar, some coset. This is equal to integral f of y, according to our original definition, chi of x plus y, y. So that's equal to integral f of y Now I can just write it as chi of x, chi of y, dy. So this I can pull it out. It looks like it, so I'm not sure. So this is chi of x. Integral f of y, y dy over g. It looks like I'm going to get f bar, sorry, f, all right, so I'm getting what? This is not f hat. So what was f hat of? What was f hat? F hat of a character. F hat on a character. Yeah, this was equal to integral f of y chi bar of y dy over g. Here I've got chi of y. So this is like f hat on this character chi bar. Which is the negative of, this is really minus chi in the group of characters, of hat of negative chi. All right. And the value, this is the, so what I want to get is eventually the following. I need to get sum f of h belonging to h is equal to, okay, so some, oh, no, we are good. I mean, this is fine. Okay. Yeah, so f of h belonging to h is equal to sum of f hat of chi belonging to h star, which is not, let's not forget this is g over h. So the character comes out, but this is the eigenvalue. Yes. So because trace is sum of eigenvalues, okay, so this by itself, well, I have to be a bit careful here, but okay, so this is not a problem. But the thing is, this shows that actually a character really is an eigenfunction with eigenvalue given by the value of f hat on negative of the character.
Why is the conjugate of the character equal to the negative of the character?
Oh, yeah, okay. So, right. So what is the addition in the group? What is the operation in the group of characters? The operation in the group of characters is multiplication of characters.
Oh,
right?
okay.
So if you multiply, and these characters are in U1. So if you multiply by its complex conjugate, you get constant 1.
Okay.
And that's the negative. I mean, or in a way, yeah, I can say it's the inverse, right? It's the inverse of this.
Yeah.
Depending if you work additively or multiplicatively. Here I was having multiplicative things in mind, but you can also do it. So what this result shows, now we are done because it shows that trace of f, actually, I mean trace of not f or f, is equal to sum of these f hat over negative chi belonging to g mod h star hat. But the summing over negatives is the sum as summing over the whole thing, because but the inversion or negation is a bijective map. So this is equal to this one. Chi. Okay, so this then we have this. Okay, so general PSF now. Okay. I think the lesson or the message that we want to remember here is that the Poisson summation formula follows really from the following fact that if you have an integral operator with nice kernel, it's self-adjoint, for example, or not even self-adjoint. It's trace, certainly trace class, if it is trace. This trace can be computed in those good cases in two ways. Either a sum of eigenvalues, which is, by the way, is a non-trivial theorem. That's Litsky's theorem, but that's another topic. Sum of eigenvalues, or as by this integrating the kernel on the diagonal, right? And this. So this is very convincing. I mean, it's very nice that this comes from some general principle. So something even more fundamental is behind the scene, which is this result about trace class operators, integral operators. Now, you see that where we are heading. We are now going to the case where G is non-abelian. Now, if G is non-abelian, there are a lot of difficulties to start with. Okay, first of all, these abelian characters, these one-dimensional objects, you know, chi from G to U1, these are not enough. I mean, there may not be even many of those. They're just few, but certainly does not capture the structure of the group anyway. So you have to look at the general representation theory of the group for the spectral side, right? So I mean, this calculation that we did here is totally breaks down and doesn't give you anything. I mean, even when G mod H is compact, there is no L2 space of characters. Well, but by Peter Wilde theorem, certainly this is not. I mean, for homogeneous spaces, there is L2 space of characters of some irreducible representations, but that needs a lot of work. We'll do it. But another thing is, on the other side, also things are not very simple, because you see what I did for the left-hand side. I calculated, just calculating this this RF, KF, XX dx over G, or G mod H, I believe, over H, sorry. This turns out to be this turns out to be a constant. This was a constant. This was easy, and then integration. But this cancellation does not happen in the non-abelian case, because we cannot transfer group elements across each other because of. So the analysis is much more subtle. You have to work with these orbital integrals, and then so there are some complications on the way, but that's okay. Okay, so we'll do that. So that's one comment I want to make before. Are there any questions? Okay, so let's now look at one example, because this is kind of nice. It's a different kind of application. So let me tell you this example. So this is application of PSF to the speed of convergence of Riemann sums. speed of convergence of Riemann sum. So that's kind of nice application. So let's assume that, okay, take the lattice. One over L Z. So you want to think of L as very large, for example, large number. I mean, right now it doesn't matter. You can take L anything, but eventually they're going to take L very large, right? And let F be smooth function. I mean, you can say F belonging to S of R, but certainly weaker conditions are enough. But I won't think about what is the maximal possible weaker condition you need, but you can work it out, and it's a very well-known result anyhow. You can look it up. So let's not spend time on that. So let's assume this is Schwarz class, but weaker conditions are possible. Then so the following, the Riemann sum. So let's do the Riemann sum. So the Riemann sum is, what is it? 1 over L sum of F of, say, N over L, N belonging to Z, is equal to integral from minus infinity plus infinity f of x plus O of x to the power minus n for any n equal to. So what does this result say? So you have a kind of lattice here, 0, 1 over L, 2 over L, so on. So what this result says is that you can compute the integral by, oh, what is this? This is wrong. I don't need that.
L perhaps?
Sorry?
Perhaps that could be L to minus n.
Exactly. L makes sense. Yes. Sorry. Yeah. Thank you. Yeah. L makes sense. L to the power minus n. Right. So you can compute the integral with high precision by summing the function on the grid like this. So I mean, this left-hand side is Riemann sum, right? I mean, this is Riemann sum. Of course, I mean, in calculus we are usually looking at finite intervals, but here is infinite interval. But okay, this is a kind of Riemann sum in some extended sense. So this is Riemann sum.
Might you actually mean summing from minus n to positive n, like capital N? Like, is capital N supposed to be in the left-hand side?
Capital N? No. N is fixed. Capital N. So we are saying for no. This is for any n. Capital N is only on the right-hand side.
Oh, you mean that the error term is smaller than any reciprocal of a polynomial?
Yes, but yeah. I want to say that. Yeah.
Okay.
I want to say that. But I have begun to be more careful than that. I want to be more careful. So let me just formulate it and we'll see if it makes sense or not. Let me start maybe even proving it, then we'll see what does this really mean, because I have to think about it, what it really means. But what is surprising is that when you define the integration, right, using Riemann sums, we just define the integral as limits of Riemann sums. But we never know how fast the sum converges to the integral, actually. I mean, how fast they converge. I mean, there is no a priori estimates. I mean, you define something by a limit. Okay, if you want to be this much close to the value of integral, what should be the size of your grid? I mean, it's kind of, we never know that, right? So that's a drawback of those kind of definitions. But this is much more subtle relation. This says that you can compute the integral by this sort of sum, and there is this error. So I have to think about what this means really now. But, so let's call it.
Question.
Yes.
This super fast convergence that you are claiming here is not really expected for like integrals of continuous functions over intervals, right? So this is much better in fact than.
Oh, this is much better, yeah. This is much better.
Because for ordinary case, I would expect that this goes like 1 over L maybe, or maybe L squared or something like that. Not any.
Yeah, I mean this is much more faster, exactly.
And do you know if there is a condition which can guarantee actual exponential decay of the error? Like analyticity or something?
Yeah, analyticity makes sense. But what could be better than Short's class? I mean, well, I mean, analytic, of course, I mean, I don't know what you mean by analytic. Could be that if the Fourier transform extends, if the Fourier transform extends to an analytic function, if the Fourier transform of the function extends to an analytic function in the complex plane, maybe entire function, maybe you can derive something like that. But it's totally, I really have no idea. Yeah, but let me. I have a more pressing issue now. I mean, what is the meaning of this? Still, I have to work it out. Okay, so let's start proving this, and then hopefully the meaning will emerge. Okay, so let's try proving this. All right, so I mean, idea of proof. Well, I mean, I can use Poisson summation formula, right? Let gamma be equal to this lattice, right? Lattice inside R. So this is our group, this is H, this is G, and the dual lattice in this case we know is LZ, right? Now gamma star is equal to LZ. This is a degree, the 1 over L, but this one is LZ, it expands. So what we have is that, so PSF tells me that sum f of n over L, n belonging to Z. Remember, we had this even for compact tori. So this is equal to L. So the normalization is L here. So sum f hat of NL, okay? And then we have got n belonging to Z again. Okay, so far we have this. Okay, so far we have this. So you divide by L, what you get? You get that if you divide by L, you're going to get 1 over L sum f of n over L. That's the left-hand side. That's the exactly Riemann sum now. Now, the right-hand side is very interesting. There is the point 0, but other lattice points get further and further away from the origin. So there is this 0, and there is here like L and then 2L, and they go to infinity fast enough or whatever. So let's not say that. So this is equal to now, I just say f hat at 0 plus sum n different from 0 f hat of n l. Okay. Now, what is this term? That's the integral, right? This is exactly the integral because f of x dx, because of definition of Fourier transform. I mean, Fourier transform f hat of, k, in momentum space, for example, this is the integral over r, f of x, e to the minus I k x dx. So, I mean, in this case, k is equal to 0, so the integration. So this is a standard, right? So this comes. Now, what about these terms? So this guy, f hat, is a rapid decay. F hat is rapid decay. It's again is Schwarz class, right? I mean, this Fourier transform sense Schwarz class is actually a, is a bijective map from Schwarz to Schwarz and plus a lot of other beautiful properties, as we know. So, all these terms are rapidly are very small. Now, how can I relate this to that? I guess I can just claim that this term is O of L to the minus n for any n equal to 1. But I'm not very comfortable with this formulation. I really have to think about this statement. Sorry. I thought I understand, but now I know that I don't understand this statement very well.
So I think the argument that you showed actually gives also the answer to my question, because we need the Fourier transform to decay exponentially, and to have that, we would need a condition of the nature that f itself extends to a holomorphic function in some strip around real numbers.
Oh, I see.
I think.
I see. F itself has to extend to a holomorphic function. Oh, okay. Well, that sounds right to me. Yeah.
Yeah, analyticity on the f side will give in a strip will give exponential decay.
Oh, very nice, very nice. Okay, yeah. So that's very good. Yeah, I mean, like so, for example, for the case of Gaussians, right? E to the minus x squared, stuff like that. Yeah. Which, of course, in that case, we know that the Fourier transform of Gaussian is again a Gaussian, so that's not it's rapid decay. But anyhow, so that's the proof. But okay, so just think about it for yourself. What does this statement mean? I'm not very happy with the statement now. Okay. Yeah, so that's an application of this thing. Of course, I mean, this Poisson summation formula. There is a not exact formulation, but there is an asymptotic version, which is Euler-Maclaurin summation formula. But that's not. I mean, it has other terms. And okay, so that doesn't follow from Poisson summation formula anyhow. So let's not discuss that. Okay, any other questions or comments? Okay, so There was one question by, before moving to this, so there was one question by Luke actually last time about the geometry of this periodic integers and periodic numbers, which is kind of nice actually. I mean, it's actually related to what we are doing to Ihara zeta function, which there will be a presentation. Nathan will talk about that, and also to, I mean, a spectral theory of graphs and trees, and to non-commutative geometry, to a lot of things. So let me just make a dent towards answering that question, because that really can take a whole, you know, I mean, few weeks discussions. But let me just give you one quick, not so quick maybe, answer. So this is geometric picture of ZP and QP. So this is kind of nice actually. It's good. Okay, so yeah, so what was ZP? We have two definitions. We defined it as completion of this metric space. Completion of metric space. Z and this distance dp, where dp of x and y is the periodic norm of x minus y, and periodic norm of an integer n is equal to, well, I mean, let me put it like x is equal to p to the minus n if x is equal to p to the n x prime, and p does not divide this x prime. So basically what you do, you just pull out all p powers that's in x. You write x as p and x prime, write it like that. And then the p norm is p to the minus n. So this is a norm, and then this defines a metric, and this metric space is not complete. This is an ultrametric. But then anyhow, so you complete it, you get this ZP. That's one definition, right? That's one definition. Now, a second definition is the following. Alternative definition is that, as I briefly touched this, ZP, you can write it as inverse limit of Z over P and Z. So let me explain. So inverse limit, we mean the following. So Z over Z, so this is P0 Z. Z over PZ. Z over P2Z, and so on. So there are these maps phi. Okay, so what we have to notice is that each of these things are rings, okay? Z over P and Z, of course, I mean, it's a ring, definitely is a ring. It's a commutative ring with 1 for any n equal to 0, 1, so on. And actually, it's a field if and only if n is equal to 1. And there's a field. This is, well, easy. Okay, so this is a ring. So this is going to be an inverse system of rings. I mean, when you have your maps, I mean, very, kind of down to earth definition of inverse system is something like this. Your maps are going in this direction. There's a general definition which we don't care. So this is an inverse system of rings. Inverse. So these phi's, maybe I should write phi n, but it doesn't matter. These phi's are ring maps. So this lemma is maybe is that there exists unique ring map phi from z over Pn z, Pn plus 1z to z over Pn z. There's a unique ring map. How does it work? Well, I mean, you can just, this is an important ring map. I mean, you can just, what you can do? Well, we have this map, quotient map. So this is the quotient map. And you just notice that this Pn plus 1z, so its kernel is Pnz. So Pn plus 1z is inside this. So you can descend, you can go to the quotient, you can go to this quotient, and then you get a map here. So still is defined. So this is, and uniqueness is easy because, you know, this ring is, you can just you look at one or something, that's easy. So there is this unique ring map for each n, and this is about it. Now, what does this inverse limit means? Well, inverse limit is a generalization of direct products. So what we mean is the following. We just take so the inverse limit by definition is the set of all sequences like x0, x1, x2, so on, such that xi belongs to z over pi z, and phi of xi plus 1 is equal to xi. So you just lift it to the next one and then keep going, right? So these are called coherent. So this is called coherence condition. This is coherence condition. And we just say this is a set of coherent sequences. Okay, of course, I mean, this is just a subset of product of all these rings, infinite product of these rings. Okay, very good. Okay, so now, what is the ring structure in this picture? Well, the ring structure is that if you have a coherent sequence, you multiply coherent sequences, you get a coherent sequence, pointwise. And addition and everything just works. So this is actually, okay, this is a subring. Of coherent sequences. Now, in terms of topology, well, I mean, these are finite spaces, and you take the Tikhonov product. Each of them are compact. Infinite product is compact. So this is going to be compact, except you have to check that this is a closed subset, which is closed. So this is closed subset of a compact space. It's compact. I mean, the topology is induced by product topology. These are called profinite spaces, means that inverse limits are finite spaces. So it's a profinite space. So this is the picture I need. So there is a lemma here, which is not difficult. I recommend you to prove it. And the lemma is that actually the two pictures are the same. So the two definitions are canonically isomorphic. So basically, from Z, you can define a map into inverse limit of Z over P and Z. You can look at, this is mod Pn maps. So you just send n to the sequence of np. Well, this by mean, this is the class of n mod P and Z. This is a map. This is a continuous map. It extends, this is a complete space. It extends to the completion here, and everything just works. There is also an inverse map. You can construct an inverse. If you have a set of coherent sequences, if that coherent sequence is finite, you can just use it to write a p-adic, base P expression of that sequence and so on. So this is, anyhow, so why I said this, because now I can tell you a little bit about this picture. So now ZP as a tree. So I mentioned this last lecture, but I went very, very quickly over this. So this was, so what is it? So as a tree, we can just look at it like this. So let's look at, e.g., let's look at the case of p equal to 2 to be very concrete. You see, you can just, so as a rooted tree, you can just start with the root, which corresponds to 0. And then you get two vertices that correspond to 0 and 1. And then each of them go to two vertices. So at this level, you have 4. These 4 points correspond to z to the power of, 2 to the 2z. These are the vertices corresponding to this. And this corresponds to z over 2z. And next stage, we get 8 points. This is z over 2 to the 3 z, and so on. Now, how these numbers should be put here? The way that you have to put the numbers here is that each of these things should form a coherent sequence. So under the lifting, so if you have a 0, 0 is here, but what goes here is that phi of this should correspond to that under this coherence. Okay, so you can label all points here, by points of z over p and z, and each element, now this is interesting, each element of zp is an infinite branch of this tree. Is an infinite branch. So points of zp, p-adic integers, corresponds to branches of this tree. For example, this branch, the way I label them, it corresponds to 0 all the way. And it's interesting, the difference between two, the distance between two elements is related to the geodesic distance. It's also interesting. So So the distance between branch B1 minus, I mean, B2, these are branches. Okay, so that's, okay, B1 and B2, there's no difference here. Okay, so now I have to figure out what's the distance in terms of this. So okay. Right.
Isn't the distance between two elements is their distance to their previous common ancestor?
Yeah, right. So I mean, I would say, first of all, I mean, the distance between, for example, what is the distance between some element and zero? For example, distance between a branch and zero. I mean, maybe distance. So let's find distance between a branch and zero. Well, the distance between branch and zero is the following. You just look at the first place that your branch starts differing from the zero branch. This is the zero branch, right? And for example, if you come here, at this point, you start branching out, the distance between this branch and zero is going to be exactly 2 to the power minus 2, or p to the power 1. So in other words, so basically, yeah, okay, so I guess one can figure this out, but I don't know how to exactly formulate it in a concise way. So I think, look, you have to think about it yourself now. So I'm getting tired now. So let's let me now